So hello and welcome to Yagio Group Design a Day Automotive. My name is Leslie Bartels, and I'm here to introduce today's presentation. So thank you for joining us as we discuss. So Axel, what's our topic today during this session?
We're talking about powertrain, about traction inverters, and the components that the Yagio Group / Chemet can offer to this special application. So it's about
Perfect.
high power stuff,
Perfect.
everything that helps the car moving.
Excellent. So a few housekeeping items before we start the presentation today. I have some information for you. So the expected duration of today's presentation is 25 minutes, followed by a 5-minute Q&A session. So in an effort to have the most optimal environment for everyone involved, attendees will be muted during the presentation. But for sure, we invite you to ask questions, and you can address your questions at any time during the presentation with the Q&A function of the Zoom session. So please, if possible, note also the slide number to your question. That'll help us to get your question answered as effectively as possible. So we'll answer your questions during the Q&A session, and if we run out of time, you can also submit questions at go.chemet.com/did/contact. So we will follow up with your question directly after the event is over. Also, this presentation will be made available for on-demand viewing after the event is over. And lastly, once Design a Day is over, you will receive an email with a short survey, and your feedback helps us to improve our future events. So thank you so much in advance for filling that out. And with this information, I'm going to hand it over to Axel. So hello, Axel, and thank you for your time today. So Axel, go ahead and take it away.
Well, thank you, Leslie, for the nice introduction. So welcome everybody to my today's presentation about powertrain / traction inverters. So just a few words for those who don't know me. My name is Axel Schmidt. I'm a senior technical marketing manager and I'm field application engineer. As you see on the age I was born, I'm a little bit older right now. I joined Chemet in 2003, so we're coming close to the 20 years. I'm a double E. And besides that, I'm in charge of the German car OEMs like Audi, BMW, Daimler, Volkswagen, and the first tire like Continental, ZF, and Active. So I'm dealing with automotive electronic all the day. And that's the reason why I picked that topic here. Besides that, I like programming, Arduino, Raspberry Pis, and also some kind of web stuff. That's just about me, a few words. And coming to the agenda of the day. So sorry for the short struggling start here. So again, for those who don't see my picture, so that was I already told a minute ago. I think we can go over that and then start with the agenda. So let's give you a short overview about the topic itself, a little bit about the ecosystem where the parts live in. And then I want to get right directly into the application. So typically it's a DC-DC boost and traction converter, so something that makes the car at the end of the day running. And then I picked up some typical questions and challenges when you start this kind of investigation to figure out the right components. And of course, I mean, US Chemet, Yagio Chemet, we want to give you some hints in which product family is probably suitable for that kind of application. And, and the two other topics are about what happens, a side effect when you start this application. So you need some kind of snubbers and then probably a filter solution. So what is a powertrain? So the powertrain is definitely everything that makes your car, your train. It could be wave runner. It could be an airplane theoretically. So everything that is in the part that makes some movement and that converts the electrical energy to a physical movement. So, and that has to generate the power and deliver the power at this part, at the motor in a way that the motor works very optimized. So you know that you have typically a battery and the battery has a limited energy. So you need to be very careful about how you spend your energy and get the maximum efficiency out of that. So how does it look like? This you see on the right side, that's a complete powertrain string. And as an electrical engineer, we typically like to talk about schematics, as you see that here. So we have this whatever battery size on the left side, which is in our case typically lithium ion, and we heard an hour earlier before from our R&D colleagues that also fuel cell is probably something that came into the game here. But at the moment in my project, we're talking about 99% about a battery, and only 1% is a fuel cell officially. And then we have the DC link cap. So why we need DC link cap? You see on the right side the switches, and then keywords like wide band gap, gallium nitride, silicon carbide came into the game here. And that is the way how we convert this DC voltage current into something that helps the motor to drive. So create a magnetic field that create a movement, and that at the end of the day will be transferred to the wheels or to the helicopter screw or whatever the wave runner has. This kind of portion that actually turns into a rotation, and that moves forward. And you see down, I draw out a little bit a control unit plus a driver, so that's a very specific topic. But we in Cameron, we don't have semiconductors. But what happens if semiconductors start switching, then for a short moment of time, the voltage from the energy source, say the battery, collapse a little bit. And that is what the DC link is doing. So he tries to catch up this collapsing battery voltage and feed some current into the system so that it runs smooth and stable, and you don't get a rocky car that bumps you forward in that case. So when we go out and talk with customers like you about this topic, we have always something we need to clarify. And believe me, I have about 20 projects running. It's already challenging to what we are talking about. So one of the most challenging things we need to figure out is the ripple current capability of the requirement of the component of the capacitor. And you see here, there's a battery. In most cases, in the meantime, we talk about 400 volt or 800 volt systems. Then on the right side, we have the switching part of the powertrain things. And in the middle is the DC link. So what you see here is, so there is one current, the total current is obviously coming from the battery. And then the ripple current is fed by the DC link, and then we have the motor current. So the total current is definitely the motor current plus the ripple current. And in most cases, it's not really clear what the customer is talking about. So you measure probably one phase leg only, or you measure 3-phase leg, or you talk about the current that goes from the battery into the powertrain application. So that is something we need to talk about, we need to think about. And also when we talk about RMS current and the values we are giving in our collateral material is based on sinusoidal waveforms. What you have in your application is typically a switch design. That means you switch on and off. That means you have certain rise and fall times of your application, as well as a pulse duration. So from here to the sinusoidal waveform, it takes some math to get the right values and to choose the right component on that. And you see here, typically that is out of an open source project competing with the Tesla drives. You have here 200 kilowatt, which is not an unusual power. So you take 500 amps and your RMS is probably in a range of 225. So typically you use a lot of caps, smaller ones, or you take one bigger cap. But actually we need to know how much current is going through the DC link capacitor. So we don't make any kind of switches, but I think it's also important to understand the ecosystem we're living in. So this is here from the Infineon friends. So I'm also in charge of Infineon as a customer. And what you see here when we talk about 400 volt or 800 volt system, it is something that built as lithium ion cell in the same technology that's in your cell phone or in your computer. actually, or your laptop. So you have to build up the battery voltage by single cells. And your inverter that converts this voltage, of course, has to operate in a certain voltage range. That means we have a maximum voltage and a minimum voltage. And the inverter has to take that and convert it into a stable voltage level that's suitable for your semiconductors in that case. And you see it's not only straightforward. So sometimes you see here on the boost converter, they put that on a certain level. That's the higher the level, the less is the current for the same power. And in that case here in this design, the customer has split up the traction inverter into two systems. So, and then you can use, component with less current capability, probably cheaper, or you can go to higher voltage level, so you don't need the same current level on that. So this is one design, and here's you see it's a C-segment core. That's a little bit on the typical 400 volt range. You see it. It's working from the operation voltage is working from 240 to 413 volt. And then, of course, when we do a design and for for a specific application, we need to know the maximum ratings. So the conditions that the component need to survive under the bad, well, the worstest condition on that case. And you see here in this example, so we have 280 amp, so 190 amp continuous power. Maximum torque is when you go up the mountains for probably a longer time, like 20 seconds, you pass over somebody, you take 280. And then we have the maximum torque that you can generate or get out of the motor is when you feed the motor with 220 amps RMS. So all this kind of calculation we need to do when we talk about with you about the right components. And that's very important because actually all this project are heavily cost driven. You probably know that very well. So we don't want to do what's called over design. So you can use more components than necessary, which will probably then have a certain impact on the cost of the application here. So one big question is ceramics. So Chemet, as well as some other competitors in the market, offering high voltage MLCCs. And what you see here is an investigation from the Fraunhofer Institute here in Germany. So they built a 200 kilowatt DC-DC converter, actually for traction system, and they built it up with ceramic chin. And the question is that how it's look like, or will we go with film capacitors as we do, or actually we're doing for, I would say, 98% of all projects we're running through. So there's some guidance we can give you, and this has also to do with the new technologies. And actually, you can, from the estimated power of your application and your voltage level and switching frequency condition, you can derive, the capacitance you need to keep the voltage level up. So what you see on the top is a formula that gives you the load. So that would be the power of the motor at the end of the day. And then you have your voltage level. And so the capacitor didn't let through DC voltages. It's only about AC voltage. That means a superimposed AC voltage is called the ripple. So you have the ripple current, and then you need to have a certain, DC bias level. And then you have this, what's called F rectifier, that is the switching frequency of your system. And traditionally, when you talk about IGBTs, so we're talking about 5 kilohertz, maybe 10 kilohertz, maybe challenging them at 16 kilohertz, so 1/6. Right now, with this upcoming wide bandgap solution, so we probably could go to higher switching frequencies. Maybe we're talking 50 or at least maybe the 100 kilohertz. And if you look on the table below here, what you see is actually let's go to the left bottom part and do the example with 200 kilowatt at 10 kilohertz. So for that, you actually need, in theory, at least 1 millifarad, 1,000 microfarad. Which is a lot. I mean, if you want to build it up with components that have only 15 or 8 microfarad, you can imagine that it's a huge number. And also the ceramic chip you see on the right side that we can offer for this kind of application, something between 220 nanofarad, so it's 0.2 microfarad or it's 0.047 microfarad. So just to get 1 microfarad, you need 4 components at 500 volt, and you need roughly 16 components at 1000 volt. So that means that will never fly because the component has a certain cost. So for this area, you probably stay with film capacitors. If you go to higher switching frequency and less power, let's say an e-scooter, an urban city car, or something that's not driving very fast and don't need that much power, and you are able to drive up your switching frequency to let's say 100 kilohertz, and you see a 15 kilowatt, then you need only 8 microfarad. And with this 8 microfarad, that's probably times 4, 32 components on MLCC. And that's probably an area where ceramic probably matters, compared to a film capacitor. So that means low power and high switching frequency is probably a targeting for MLCC. And for the low switching frequency and very high power, we still will be with film capacitors for, I think, for quite a while until we can change that. So why not the other things? So why only film and COG? Obviously, when we talk about this kind of application, we talk about a lot of power. We don't talk about 5 volt, 1 amp, which give you 5 watt. So the power loss leads, of course, to the self-heating. What means, so the temperature rise of the component is somehow I square times the ESR, so the ohmic resistance of the component at a certain frequency, and the thermal resistance of the component. And then the ESR, you can derive that typically from the dissipation factor. So that's the way how you, if you don't have the specific information getting from your supplier / from us, so we can give you ESR for every frequency which is suitable. That's typically up to self-resonance. And then let's assume we have a 500 microfarad, 325 amp at 30 kilohertz. And we look on the dissipation factor. And from the dissipation factor, we can calculate the power loss. And then you see when you use an aluminum electrolytic in that case at 30 kilohertz, so your power loss would be 112 watt, which is a lot. I mean, you need to spend that much in cooling that probably better prices for aluminum electrolytic will be eaten very fast. And then we have the polypropylene, which is where we have, I think, at the moment, most of the project we are running through. And you see the dissipation factor is much lower. It's 0.05% or 0.07 at 10 kilohertz. So the power loss would be only a 0.6 watt. And even in this kind of application, we're talking about really high sophisticated cooling systems. If you look on polyester, which would give you the benefit of getting a higher temperature, so 125, and actually we're targeting 130 and even a little bit above. But then, coming from the 0.6 for polypropylene, we're talking about 16.8 watt because the dissipation factor is much worse. It's 10 times higher or 20 times higher than the polypropylene. And that's a major reason why most customers and most projects use polypropylene. And then for the COG, we are in a range of 0.3%. For the dissipation factors, that means we have 5.6 watt. But we can drive MLCCs to higher temperatures. So COG is capable to handle 150 degrees Celsius. So that means it's a very thermal robust part. So we can spend a little bit more on power loss in terms to polypropylene, which is very sensitive for temperature or over temperature condition. And then you see an X7R, you have 2 to 5% depending on your rated voltage. So your end up here is 30.3 watts. So it's also something typically you will not consider because the power loss is simply too high for that. So if you're working in a big company, then you have the ability and talk with Kemet directly. But I can tell you, actually, this department is doing this, what we call custom rig capacitors. So we do a custom specific design. So we need to have a certain volume running. That means something with 100,000 pieces a year and more. And then this kind of development takes typically, I think the last one took 2.5 years actually. But I think 1 year is actually the minimum. And we talk about a high invest. So to get this customs to them, so you need tools and dies and cavities and a lot of effort, a lot of simulation. So we have some high sophisticated programs, and then we can simulate the temperature and the vibration. And then we need to confirm the simulation. We do some evaluation. So we build some samples. In the meantime, we only build 1 or 2, and the more or less at the end of the day. But this is only if you have a really high volume, or at least a project targeting a very high volume, and you are able to spend investment in a range of 200,000 to 500,000 euros for that case. What is the challenges in this? Definitely, or why we can do it very simply, is about the coefficient of thermal expansion. So that's the CTE. And you see here the polypropylene we are using was that kind of film capacitors. So we're talking about 160 ppm per degree C. And then copper is 16. That means we have some kind of stress. So if you do thermal cycling, which is typically required in the automotive industry, then we tear off here very easily after a few cycles, this kind of design. So it's a very special design. I cannot show you, that's business confidential. But actually, I can tell you it's not very easy to survive and to pass this kind of thing. So what are you doing if you're not working in a big company and you have to have probably smaller project? And I really highly recommend to go with this D-Ceiling C4AQ family. That's actually the best you can do, because I think the price is something a few, definitely less than 10 euros. And you get 130 mic at 400, 500 volt system. In the meantime, you can get up to 230 microfarad if you suffer a little bit in the temperature and the maximum temperature. But also for the higher voltages, the 800 volt system, we're typically targeting this 1100 volts. So you have really a lot of options, and you can easily modify or build modular systems. You have maybe a 10 kilowatt and a 20 kilowatt, and for the 10 kilowatt, you need only a 4 component, and maybe for the 20 watt, you need 8 components. So that is, I think, would be my highly recommendation if you start this and not working for the bigger companies and directly with the OEMs. Actually, one topic that's also very important is lifetime. So of course, you have certain requirements for that. I need to speed a little bit up because I'm doing this things. We have a little bit issues here. So at the end of the day, when you see the catalog values, that's not written in stone. That is something that is a 3D space. So lifetime, temperature, and the applied voltage level are something that influence or impact each other. So in that case, if you have maybe 85 degrees C or 105 degrees C, so we can play a little bit around, and that is just call us if you need some help on this and figure out the lifetime and the voltage level, and then probably helps you to save some of the components. Other thing that the semiconductor guys try to eliminate quite a while is the snubber. In some cases they're successful, but what I see in most cases they are not. That means we can also offer you snubber capacitors that are able to catch up the overswing that typically happens when you switch an inductive load, for example. And so we have also components that are ACQ200 qualified, so it's adapted in the automotive industry. So here you see the DVDT is one of the key component here that's actually we are working on and drives that limit a little bit above, as well as this, sometimes people are struggling about with max K0. And you see here, we have the time to work through that, but if you have any questions, then let me know, then we can do that and can give you some guidance at the end of the day. So DVDT is the key for the pulse capacitors, which are also in this X and Y. And so we have two families here. It's a R75H and an R76H, and H stands for high voltage, high temperature. And that means they're capable to handle 125 degrees C, which is pretty good on that case. And you see here, just in some cases, people talk about 11 kilovolt per microsecond. That's the maximum we can offer to you. And then we have that's comparable to 11 volt per nanosecond, or if you like this term, 11 gigavolt per second. It's all the same. It's just different expressions for the same thing. And that is our recommendation. Go with R76. That is the newest and latest generation, and they really had excellent results with snubbering. For those that are not very familiar with all this electrical things behind, so on the left side you see a sinusoidal waveform, and then here you see the frequency, the magnitude, and see there's only one peak here. That means it's really a single frequency. What happens if you do switching is you see here it's going up here to the trapezoidal waveform, and this trapezoidal waveform here causes a lot of so-called higher harmonics. There's a law that means if you add them all up, you end up with a square wave here. And that is called, or is found under the term Fourier transformation. And that's the reason why we need to come up with some kind of filtering, because we don't want to have this red overswing here, and that cause a lot of issues in terms of EMI. And that's the reason why we also can offer capacitors for filtering. And you see here we have a Y capacitor that's going from one hotline to ground. And then we have the X capacitor that's going from hotline to hotline. You can understand this must be very carefully. This is a safety design, because if that part would go short, then you have the chassis 800 volt, for example, or in that case, you short plus and minus. That would be very ugly failure. So this part are really designed to get an open failure mode. And then here we have the DC link capacitor. Here, actually, the recommendation was the C4AQ. Then the snubbers are 75 or 76. And we can also offer differential mode and or common mode chokes, which are in 99% custom for automotive application. In that case, you really talk to Chemet people, talk to FAE or your sales guy. We can link you to our R&D services and create a custom part for that. So here again, I flip over again. It's an EMI filter that typically at the beginning from the energy source to the switching unit, to the booster, or to the inverter system. So we have all these components here available. One thing here is a special thing, the common mode and differential mode. So we have really custom designed, and what we can do, and which is really exciting, is we can combine a common mode and differential mode within one component. And we do it by a really special design. Here you see the small nose that allows us to build one physical component with two functionalities on that case. And with that, sorry to be a little bit fast, but time's running out of that. Hey, Leslie, are there any questions or we can answer? Or
Axel, first, thank you so much for your time. That was great. I don't see any questions in the Q&A box yet. Feel free to, if you do have questions regarding this presentation or any of the Design a Day presentations, go ahead and submit them at the link that Axel is sharing right now. But I think we're good to go with questions for now. Yeah. So
so many the timeline,
Yeah, no, you ended right on time. So thank you, Axel. And thank you everyone for attending this presentation of Design a Day. And again, as we didn't have much time to answer questions, feel free to submit them at go.chemet.com/did-contact, and we'll be sure to reach out to you with answers to your questions. So please be sure to check out the other great presentations today, everyone. And thanks again.
Thank you, everybody. And maybe get in touch with me if you like. Thank you. Take care. Bye-bye.